today's lecture we will discuss about A to D converters. So, in this we focus mainly on not how to construct A to D converters, how to use them, how to make error budgeting. Of course, we will discuss something about how to use the A to D converter using microcontroller and so on. So, our topic would be analog to digital conversion. Our topic would be analog to digital conversion. So, basically we call A to D, ADC. Now, basically what is done is that we have a analog voltage and then that voltage has to be converted into digitized. So, essentially that this is given to ADC and then the output comes in digital form, say 8-bit converter, means then you will have 8 lines of digital bus. So, 6, 7, 8. So, 8-bit converter means analog value corresponding to analog value, you get a digital output of 8-bit. So, this we call 8-bit converter, and this analog conversion is taking place with respect to reference voltage. That is, we should have a reference voltage, we will have a V input voltage and output is digital. So, what really happens is that in the A to D converter, if V in is equal to V reference, if V in equal to V reference, then if we have a 8-bit, all 8 bits will be high. For example, if I have a 8 bits, then this is MSB and this is LSB. Then for V in is equal to V output, V in is equal to V reference. For example, if I have 1 volt reference, 1 volt and V in also 1 volt, then all the 8 bits will be high, all bits are high. For V in is equal to 0, then you will get all 8 bits are 0, all bits are 0. That means for 1 volt or 1 volt input, we have a change of all zeros to all 1. So, if we take a digital level, binary level, total binary level is actually 2 power 8, that is equal to 256. So, essentially for 256 levels you have 1 volt difference. That means 1 LSB, that is what is the one, suppose if 1 least bit, that is if it is LSB and if this is MSB, for 1 LSB to change the required voltages 1 volt divided by 256, that is nearly equal to 4 millivolt. So, for every 4 millivolt roughly you will have 1 LSB change. Other way around, if the input is say 4 millivolt, if the input is 4 millivolt, the corresponding digital output would be only last bit alone is coming high. So, like that we can have a digital output corresponding to the analog input. This only we call it A to D converter. So, we use the term LSB. So, LSB is the least significant bit. So, for 1 LSB what is the voltage required? So, for 1 LSB, the required voltage is V reference by 2 power n, where n is the number of bits. So, if it is 8-bit converter, then it is actually V reference divided by 256. So, 1 LSB value tells us what is the minimum resolution that we can get in the converter. So, 1 LSB gives us the minimum resolution that one can get in using this converter. Resolution one can get using this converter. Of course, this depends upon the reference voltage. If the reference voltage is different, for the same converter you will get a different resolution. Converter. So, the LSP value depends on the reference, depends on the reference voltage. So, let us see if we are using the, if I want to convert analog into digital, what are the options that is available, so that I will get a digital value corresponding to the analog input. So, let us see what are the types of converters available. Now, if you look at this, the types of converters, now one is we call that is a dual slope AD converter, which is very popular converters, dual slope ADC. Then the second one is actually successive approximation A to D converter. That is the second type. Third popular type is actually flash ADC. And now the fourth very popular one that is available in the market is sigma delta ADC. So, we see at this point of time these 4 different types of A to D converters, and then we see how it is working, what is the errors associated with each one, and how to use them for our best use. So, we will start our discussion with the dual slope A to D converters. So, we will pick up the dual slope AD converter and then discuss about its usage, and then the error associated with the dual slope converter and so on. Now, in the dual slope ADC, the classical construction technique used is that you take operation amplifier, and then we will have a capacitor connected here as a like an integrator. Then we will have a input voltage V input, which is to be digitized, which is a digital voltage, assume it is positive, and they have R in. Then we will have to this switch, then we also can connect through a switch, of course. So, the switch can be connected to this. So, what I can do is I can have a switch here, connected to this. I can have another switch, this can be connected to V reference, and then through another resistance it is connected to the same. We call this is R reference resistance, then this is capacitor C, and this is our output. This is actually the circuit diagram of a dual slope A to D converter. Now, let us see how it is working. Now, we name this switch as S1 and this one as S2. Now, if you look at the circuit, we have 2 conditions, that is when S1 is on, for example, S1 is on and then S2 is off. We take the condition, first condition, that S1 is on and S2 is off. So, this is on, and then assuming C is empty. Assuming C is empty, we will take up this consideration, that is S1 is on. So, under this condition, that when S1 is on, then since this at 0 volt, this also has to be at 0 volt. So, when S1 is on, I will call I input current, that is flowing through I input flows through the resistance R, through the resistance R in. because since plus and minus terminal are minus terminal is at 0 volt. So, minus input is at 0 volt. So, we can say what is the current through R in. So, what is the current through R in that we can find out. So, the current through R in, I can write it as, so current through I input current, that would be equal to V in divided by R in, because minus terminal is at 0 potential, that is the current that is actually going through this. Then if you look at the current through C, then the corresponding current through C would be same. So, that is equal to current through C. Current through C. Now, the current through C is known. So, the capacitor will be keep charging, that is when once I connect S1 on and S2 off, then the voltage source V in actually charges the capacitor C. So, essentially the input that is the input source, source voltage charges the capacitor C, at a constant rate, So, the capacitor voltage is built up. So, we should know at the end of the time what will be the capacitor voltage. So, capacitor voltage can be obtained, capacitor voltage will increase with the time, but the capacitor voltage is same as the output voltage. So, the output voltage is equal to the output voltage, that is equal to capacitor voltage. So, the since the capacitor voltage is increasing, output voltage also increases with the time. So, if you look at this in the for the given circuit, that what really happens is that if we plot in terms of time versus output, if I plot, that essentially the output voltage goes in the minus side, because V is a plus. So, the output voltage will be increasing with the time. So, this is the time and this is the output voltage. In the minus side it is increasing, and this slope is determined by the current, essentially V in by R, that is the current it decides this one. So, if we write the equation for capacitor voltage, so we can use capacitor voltage can be obtained, capacitor voltage actually is can be obtained by Q is equal to IT. So, Q is equal to CV. So, we can write IT equal to CV equation we can use and find the capacitor voltage. So, capacitor voltage actually or output voltage is actually given by IT divided by C. So, the I is actually given by I is equal to V in by R. So, V0 actually is given by V in by R in, then into T divided by C. So, that is the capacitor voltage or the output voltage, that is the output voltage, and that is same as capacitor voltage. So, the output voltage and since it is the invert due to op amp inversion, we get a minus sign due to op amp inversion, due to op amp inversion. So, that V0 is coming as V in by R in is I into T divided by C, that with the minus sign. So, that goes to minus side. So, the minus sign is introduced to take care of the inversion. So, we take this, that is the equation for V0. Now, what is that it signifies? That is if I have the if I have input voltage, I make the switch on for some time, that switch S1 on for some time, and then I see that the output voltage increases with the time, the output of the op amp increases with the time. So, essentially speaking, if you look at the our circuit, that when S1 is on, the output voltage slowly increases towards minus side, and then it continues for a time. Now, you keep this switch S1 on for a fixed amount of time t, so that the output voltage reaches some value and then it stops. So, what essentially happens is I will keep the I limit the time t, that is, this is voltage and then this is the time. So, the output voltage goes here and I keep this one only for t on, this is t on. So, t is actually limited. So, keep S1 on, keep S1 on only for a fixed time, that is t on. After this time, then after t on time, switch off S1, switch on S2. So, switch off S1 and switch off S2. Now, once S1 is switched on or switched off, the charging stops, because the if you look at our circuit that we had, that we have S1 on, and then that is charging through this V input, and then we see the V reference that actually connected through S2 to this S1 and S2, and then our capacitor is connected here. So, when S2 is on and S2 is off and VR is minus V had given. So, minus fixed voltage is given. Now, you will have a current through this R in R reference. So, that current will be opposite to that of the original current. Switch S1 is connected to switch S2 is connected to V reference, through the reference resistance R reference. Now, because of that, the current through the R reference is now opposite, and then the capacitor discharges. The current through RR is opposite to that of R in. So, capacitor C discharges now. Discharges. So, capacitor, so the output voltage start coming down. So, the output voltage V naught will start coming down. Keep S2 on, so that V0 becomes 0 after some time. So, essentially what happens is that if you look at the our original curve, that is the time versus voltage, that first even S1 on, it was going down the minus side, and then it keep decreasing at a rate. So, here actually is t on time and this is t off time, here S2 on, and the output still it is S2 on, keep it on, still it reaches 0 volt. So, when it reaches 0 volt, then again you restart and start S1 and S2. So, you keep S2 on, still it reaches still the output voltage reaches 0, that is capacitor fully discharges. So, now if we see the discharge equation, that comes because discharge current I discharge is actually is nothing but V reference divided by R reference. So, the same using same equation I t is equal to C V, the capacitor equation, that you will get the equation that is time to discharge we can write out. So, what really happens is that the voltage, that again the same equation comes I t by C is equal to V naught. Now, since the discharge charge that went there to at the time when S1 is on to the capacitor must be equal to charge that went out when the capacitor completely discharged. So, total charge during S1 on was total charge delivered to C when S1 on is equal to I into T, T, and then that is equal to V in by R into T. So, that must be equal to total amount of charge that left. So, total discharge current, total, that this is on time. So, total discharge is given S2 on, that is equal to V reference by R into T of time. This is R, this is R in. So, this both must be equal to equal. So, what we can do is that we can equate these two, that is because total charge must be equal, total input charge must be equal to total output charge. That actually makes, so V in by R in into T on must be equal to V R by reference resistance into T off. So, essentially if R in is equal to R in is equal to R, then actually we will get V in by V R will be equal to T off by T on. The ratio of the voltage is actually now controlled by the ratio of the time, that is what was the on time and what was the off time. If this is fixed, if T on is fixed and then V R is fixed, then V 1 must be equal to V 1 is proportional to T off. So, this is that means the input voltage is measured in terms of time. So, if I can have a clock to measure the T off time and keep the T on constant and keep the V R constant, then my input voltage can be measured in terms of off time. So, off time can be obtained using a clock. So, you will get a digital output in terms of number of periods, because I can have a digital clock and then that can be measured in terms of number of pulses I can count and that T off period can be measured using the T off period can be measured by counting the number of pulses. So, that way the digital output can be obtained for a corresponding analog input voltage. Now, see this, the the capacitor value is immaterial, because the capacitor value is not appearing in the final equation. So, even the drift in the capacitor, short term the long term drift of the capacitor is not a issue as far as accuracy is concerned. The capacitor value, the C is not appearing in the final equation. So, the long time drift of the capacitor is not a issue. So, it is not a problem even if the capacitor slowly drifts due to temperature. Temperature drift also not a issue. Temperature slow drift of the capacitor C. So, the slow drift of the C due to temperature is not a issue, because T on and T off are in milliseconds. However, there is one issue with this capacitor C, that dielectric absorption of the capacitor is a major concern in this application. So, even though the capacitor temperature drift and long term drift is not an issue, the dielectric absorption of the capacitor is a major issue. So, the dielectric absorption of the C is a major issue. Actually, the dielectric absorption creates a problem, in the sense that the dielectric absorption is explained like this, that if I have a capacitor, if I charge it to some voltage V, and then if I discharge it quickly by putting a very low resistance, then you will find that after some time, that when after removing this resistance, if I remove this resistance, then I will find that part of the original voltage appears across in the capacitor. So, we can show like this. If you are new to this, then you can follow this explanation little bit, which will be of which will be of help to you in the later case. That what you can do would be that if I take, for example, if I take a capacitor and charge it to say 10 volt. Then the second step would be, I remove this, what I do is I will take this capacitor, put some few ohms, 1 or 2 ohms, and leave it on for few seconds, allow the capacitor to discharge, allow the cap for discharge fully. Then third step would be, from here, that what you do is you actually make this is first step, then second you discharge. Now, after few seconds you remove the capacitor resistance. So, remove the third step, actually remove the load. Then the fourth step would be connect the meter, after remove the load, then connect the meter across this, voltmeter across this, good voltmeter. So, the fourth step, remove the load, then now connect the high impedance multimeter. High impedance multimeter, volt mode, high impedance multimeter, that is in the voltage mode. Now, you will find that with the time the voltage is building up with the time V is increasing. That is, some of the charge reappears on the capacitor, charge reappears in the capacitor. This is called dielectric absorption. This is called dielectric absorption. For example, for electrolytic capacitor, this is about 10%, and if you take a ceramic, this is this will be around 1% level. For electrolytic capacitors, cap, it is about 10%. 10% of the original voltage will reappear. For ceramic, 1 to 2%. For plastic film capacitors, it is less, that is 0.01% to 0.1%. For example, polycarbonate have very low dielectric absorption. So, what is the problem? What is the problem with this dielectric absorption in the case of our dual slope AD converter? So, in the dual slope AD converter, if we charge the capacitor first, we are charging the capacitor first with the V input, and the capacitor is charged to minus voltage, that is output voltage is minus and the capacitor anyway charged. Now, we are making the S1 off and then making S2 on. So, when S2 on, so we have S2 on and minus V reference is given, V reference minus V reference. Now, the capacitor discharges through this. Now, if the input S1 is very small, then this voltage would have been charged to some value and then it would have been discharged quickly by S2. The next voltage actually appears very large, or for example, next time that V in had changed, then it will charge to very high voltage, then it will discharge quickly through S2. And the third time when again the low voltage comes low, then when it is start charging, you will find that part of the earlier voltage is reappearing. So, like it is like this. So, if initially assuming first V in is large, V in is large, then cap C will, then C will charge to high current, then C, then C will charge high voltage. C will then you discharge quickly, then S2 discharges C quickly. Now, if the input voltage are changed, the input voltage is changed to a lower value, let us say from 1 volt to 10 millivolt or so. Now, when S1 is on, this 10 millivolt will deliver small charge, will deliver small charge to C, but in addition part of the earlier charge will reappear, part of the earlier earlier charge also will reappear, start reappearing. So, this will affect the measurement now. So, this will reappear due to electric absorption. This will make the reading, this will make our measurements wrong. So, this will make our measurements wrong. Measurements to go wrong. So, if the capacitor, if the dual slope ADC converter had to work, the capacitor should have very low dielectric absorption. So, it is essential. So, it is essential that C is having very low dielectric absorption. So, dual slope converter, and the other main advantage of dual slope ADC converter is it is not sensitive to noise. Dual slope converter sensitive to noise issues we discuss, noise issues in dual slope converter. Dual slope converter is not sensitive to external noise. This is because if you see our circuit, we have input coming to this through a resistance and then another switch, and then you have a capacitor C. So, assume this is V reference minus V reference and this is input R input. S1 is on for a particular amount of time. For example, if I do not want 50 hertz noise, because if the input signal is having a 50 hertz noise, then I can show that the V input consists of DC plus AC source, which is a 50 hertz. So, the current that is going through S1 or one consists of AC current plus the DC current, both are actually flowing here, and then if the T on is integral multiple of noise frequency or noise time period, then noise is averaged out. That is like this. Suppose if I have a DC plus AC time versus voltage by plot. So, DC is in this, and then over that AC is going. Essentially, the current through this R will have when the AC voltage positive peak, it increases the current. When the AC voltage negative peak, it decreases the current. So, the net average charge delivered to the capacitor will be 0 if the on time is integral multiple of the noise time. For example, this is one cycle. If I make it, for example, on time T on is few cycles, say to remove 50 hertz noise. If T on say equal to 60 millisecond, 3 cycle time, because T on is fixed. So, I can fix the time. So, if I keep the T on as 60 millisecond, then you will get average of 3 AC cycles. then your average current of 3 AC cycles is obtained, then averaging is done for 3 AC cycles. This will make the output insensitive to noise, because average charge delivered would have been, average charge due to AC is 0. The average charge due to AC component is 0. So, as long as T on is integral multiple of noise time period, then the converter is insensitive to noise. So, the converter is the ADC is not sensitive to input noise. This is the special merit of this dual slope ADC converter. This is the merit of the dual slope ADC. Of course, this is valid only if it is integral multiple of noise frequency, noise time period. Even otherwise also, even if it is not integral multiple, we will get some averaging, and only very small part of the AC signal will produce output voltage, and that may not be very significant. So, this kind of converters are very good from the noise rejection point of view, but they are very slow, because you had charge per integral multiple of time, and then integral multiple of noise frequency, and then you also have to wait some time to discharge. So, the conversion is very slow. The disadvantage conversion is very slow. Very slow. Advantage, insensitivity to noise. So, these kind of converters are even though it is slow, they are that is quite enough for display purpose. So, these converters are used, this type of converters are used for LCD display, etc. So, because anyway display cannot be updated very rapidly. So, at the maximum 8 to 10 conversions are possible, at the maximum 8 to 10 conversions possible. So, that is good enough for display. So, most of the displays today they use this dual slope ADC converter. So, this is very popular ADC converter, and they almost all displays use this ADC converters. All displays use this type of converters. So, this kind of converters are available for 3.5 digit, 4.5 digit, 3 digit, and so on. For the use as single chip, it is available, one can use them. For example, popular 3.5 digit display industrial 7107, 710 industrial converters are this type, and you will get a ready made module actually with a display. So, you have a display unit with the converter inbuilt. So, you have a input is given here, V input is given here, and then the chip actually does the dual slope converter, and it needs a inbuilt reference, and it needs a minus supply as well. You need a plus supply, and then this can be directly interfaced with the 7 segment LCD display. And this is the main converter. So, this is available as an integrated model which one can use for displaying the values, displaying the analog value into digital value. And this also can be used other applications wherein we want to digitize, but the noise should not enter into the instrument. But only thing is it will be slow. For example, we can use a microcontroller and do this kind of conversion. So, microprocessor based dual slope ADC converters or microcontroller based. Converters, slow ADC, or when we are using a microprocessor based system, one need not look for this dual slope ADC converter, one can easily achieve this kind of conversion function using a microcontroller. What can be done is, for example, there are various techniques it is done. So, in the case of if you have a microcontroller, we can, if I want to digitize the analog voltage, the simplest thing they can think of would be, if I have a microcontroller, for example, I give the supply voltage, then what is done is the V input voltage which is to be digitized can be given through a resistance and through a capacitor, and it can be connected to one input port, for example, V 1.0 I can connect to this. Now, that is V in. Now, what we can do is that I can have a switch connected across this to discharge. So, I can have a switch connected here, that is a MOSFET switch. Then that can be connected to another port, say P 1.1. For example, if I take 8051, I can have such a arrangement. What is done is that I can have switch S1. So, first to discharge the capacitor C fully by switching on. So, you discharge C, discharge C, discharge C by switching on S1, switching on S1. Then start the timer, in microcontroller, and simultaneously switch off S1. Now, the input voltage will charge, because now S1 is off. Now, the whatever current coming from, so V in, that will charge the capacitor C. Now, after some time that capacitor will charge to some value. Allow this S1, allow this off condition for some time. Now, the capacitor voltage will slowly increase. Now, the capacitors C will slowly increase. Capacity will slowly increase. Now, we can have for example, many of the microcontrollers have inbuilt comparators. So, we can have this, if it have been given to the input comparator, and then this is given as a V reference, it is given to a V reference. So, if this is given to the inbuilt converter, if the input is given to the plus input of the microcontroller comparator, now the capacitor will charge now the capacity will slowly increase, capacitor C voltage will slowly increase. The comparator in the microcontroller, the comparator in the microcontroller will change state, once the capacitor voltage goes above reference fixed inside the microcontroller. Once state change occurs, once state change occurs, and in the comparator occurs, the timer is stopped. That is, we had charged the capacitor for a certain amount of time to reach the value, to reach the fixed voltage value, and then the timer is stopped. So, the time period can be used to calculate the input voltage Vn. This is because the capacitor charges exponentially to the V reference. So, essentially what is happening is, if you plot the equation, that what happens is the time versus capacitor voltage, cap voltage, if you take, is exponentially going up. So, we have started the timer here, timer is on, here, and then it is a V reference, this is a V reference, here V reference. If the V reference is this, then this is the once it capacitor voltage, this is the capacitor voltage. Once the capacitor reaches the V reference, it is stopped. So, this is off, here timer off. So, this is the time taken to reach the voltage VR. So, this T0 period, the period T0 gives you gives you the input voltage. But this is not a dual slope converter. This is not a dual slope converter. The capacitor drift, resistance drift, all will give error. The capacitor drift, resistance drift, all will give error. Of course, the noise averaging is there, all will give error. The second one is the noise averaging benefit is there, noise averaging benefit is available. But not completely, not completely, because T on is not fixed, it changes with the input voltage, it changes with the changes with input voltage. Nevertheless, this is a poor man's ATD converter, which is used in the microcontroller world extensively. The equations are there. For example, almost all the microcontroller manufacturers provide this kind of conversion solution. For this purpose only, most of the microcontrollers have inbuilt comparator. You can also put the comparator outside, and then you can switch on and off the timer and realize the A to D function even if you do not have a comparator in the microcontroller. But this controller can be improved. This conversion, converter can be improved by modifying the circuit, Of course, some extra component we put modifying the circuit. We can also obtain dual slope ADC function using this type of converter. Of course, we will modify the charging and discharging method, so that one can use in the microcontroller world the dual slope converter, because dual slope converter has many advantages. As I said, the capacitor is not involved in the measurement, and also noise is not a serious problem. So, we will discuss about the modified dual slope ADC converter in the microcontroller environment, and how that can be used in the microcontroller applications. We will see in the next lecture. Thank you.